Hello viewers, I Ch05 welcomes you to the episode on normal distribution. In this episode, we shall discuss briefly the introduction of normal probability distribution. We'll discuss the probability density function of a continuous random variable, properties of normal distribution, standard distribution, normal approximate to the binomial distribution and its theorem, and also the normal approximation to the Poisson distribution and its theorem. Before proceeding to study the various topics of probability, we'll first acquaint ourselves with the terms which are going to be used in the discussion. We discussed two useful theoretical probability distributions, the binomial and the Poisson. For these distributions, the random variables that we considered were discrete. Now we shall concern ourselves with the probability distribution of a continuous random variable. A random variable is continuous if it can assume any value in some interval. A continuous random variable usually represents data that are measured such as heights, weights, distances, and time. The probability distribution of a continuous random variable is called a continuous probability distribution. The most important continuous probability distribution in the entire field of statistics is the normal probability distribution, or simply the normal distribution. Its graph, called the normal curve, is the bell-shaped curve as shown in figure 1. The curve extends indefinitely to the right and left and never touches the x-axis. Let x be a continuous random variable. A function y equals to f of x is called a probability density function, or simply density function for x if it satisfies the following properties. First one, f of x greater than equal to 0. Then f of x integration of fx dx from minus infinity to plus infinity. Third, probability of a lesser than equal to x lesser than equal to b is equal to integration of f of x dx from a to b. For example, consider an experiment in which a number x is randomly selected from the interval 0 to 1. Then x is a continuous random variable such that probability of a is lesser than equal to x lesser than equal to b is equal to length of the interval ab, which is equal to b minus a, where a and b are in interval 0 to 1. We now define a function f of x as follows. F of x is equal to 1 if 0 is less than equal to x is less than equal to 1 and 0 otherwise. We shall show that f of x is a density function of x. First, since f of x is either 0 or 1, we have f of x equals to 0. Next, since f of x is equal to 0 for x outside the interval 0 to 1, we have now integration goes from minus infinity to plus infinity. F of x dx will be equal to integration goes from 0 to 1 of 1 dx will be equal to x going from 1 to 0, which is equal to 1. Finally, to verify that probability of a lesser than equal to x lesser than equal to b is equal to the integration goes from a to b of f of x dx. We compute integration of a goes to b f of x dx equals to integration of 0 to 1 of 1 dx will be equal to x going from a to b, which will be equal to b minus a, which as stated in equation 1, probability of a lesser than equal to x lesser than equal to b. The normal distribution is the most important continuous probability distribution whose density function may be approximated by the bell-shaped curve shown in image 1. This curve, called the normal curve, is a graph of the most important of all density functions, the normal density. In 1733, French mathematician de Moivre derived the mathematical equation of the normal curve. A continuous random variable x is called a normal random variable or has a normal distribution if its density function is given by f(x) is equal to 1 by sigma under root 2 pi times e to the power minus 1 by 2 times x minus mu upon sigma the whole square. Here x goes from minus infinity to plus infinity. The parameters mu and sigma are the mean and standard deviation of x respectively. The normal distribution is often referred to as Gaussian distribution after the German mathematician called Friedrich Gauss 1777 to 1855, who also derived its equation from a study of errors in repeated measurements of same quantity. Symbolically, if x has a normal distribution with mean mu and standard deviation sigma, we write x as a normal distribution with mean mu and sigma. Some authors use the notation n in bracket mu sigma the power 2. Image 2, normal curves with mu 1 not equal to mu 2 and sigma is equal to sigma 2. Each choice of values for mu and sigma determines a different normal curve. The value of mu determines where the curve is centered. In image 2, we have sketched two normal curves having the same standard deviation but different means. The two curves are identical in front but are centered at a different position along the horizontal axis. Further, the value of sigma determines how spread out the curve is. For example, image 3 shows two normal curves with the same mean but different standard deviations. This time, we see that the two curves are centered at exactly the same position on the horizontal axis, but the curve with the larger standard deviation is lower and spreads out farther. We list the following properties of normal distribution. The normal curve is bell-shaped and is symmetric about the vertical line through the mean. In other words, the mean is at the center. The normal curve never touches the x-axis and extends to infinity on either side of the mean. In other words, the normal curve approaches the x-axis asymptotically as proceed in either direction away from mean. 3. Irrespective of the shape, the total area under the normal curve and above the horizontal axis is always equal to 1. 4th, no portion of the normal curve lies below the x-axis. 5th, the normal distribution is unimodal, the only mode occurring at x equals to mu. 6th, it has its mean, median and mode at the same point. 7th, the area under the normal curve bounded by the two ordinates x equals to a and x equals to b equals the probability that the random variable x assumes a value between x equals to a and x equals to b. Thus, for the normal curve in image 4, probability of a lesser than x lesser than b is represented by the shaded region. The first and the third quartiles of a normal distribution are equidistant from median. That is, q1 minus median is equal to median minus q1. Next, the first and the third quartiles of a distribution are given by q1 equals to mu minus 0.6745 and q3 is equal to mu plus 0.6745 sigma. The mean deviation MD about mean or median for a normal distribution is given by median MD equals to 4 by 5 sigma or MD equals to 0.7979 sigma. The quartile deviation QD for a normal distribution is given by QD is equal to Q3 minus Q1 by 2, that is equal to 0.6745 sigma, which is approximately equal to 2 by 3 sigma. Also, QD is equal to 5 by 6 MD. Since CQD is equal to 2 by 3 sigma, that is equal to 4 by 6 sigma, which is equal to 5 by 6 times 4 by 5 sigma, that is equal to 5 by 6 MD. QD is to MD is to ST is 2 by 3 sigma is to 4 by 5 sigma is to sigma, that is 2 by 3 is to 4 by 5 is to 1, or QD is to MD is to ST is 10 is to 12 is to 15. The various descriptive measures of the normal distribution are mean equals to mu, standard deviation equals to sigma variance, or mu2 is equal to sigma to the power 2, mu3 equals to 0, mu4 equals to 3 sigma to the power 4. Moment coefficient of skewness or beta 1 is equal to mu3 square by mu2 cube equals to 0. Moment coefficient of kurtosis or beta 2 is equal to mu 4 by mu 2 square, which is equal to 3 sigma to the power 4 divided by sigma to the power 4, which is equal to 3. The normal curve has its point inflection at x bar plus minus sigma. The standard deviation of a normal distribution is related to area under the normal curve as follows. First, about 68.27% of the total area under the curve is covered from mu minus sigma to mu plus sigma. So see image 5 for that. Second, about 95.45% of the total area under the curve is covered from mu minus 2 sigma to mu plus 2 sigma. Third, about 99.73% of the total area under the curve is covered from mu minus 3 sigma to mu plus 3 sigma. Next, the sum of the independent normal variates is also a normal variate. In fact, if x and y are independent normal variates with the mean mu1 and mu2 and variances sigma 1 square and sigma 2 square respectively, then x plus y is also a normal variate with a mean mu1 plus mu2 and a variance sigma 1 square plus sigma 2 square. If z is a normally distributed random variable with mean mu equals to 0 and standard deviation sigma equals to 1, then z is called the standard normal variable or has a standard normal distribution. Thus, the density function of the standard normal variable z is given by f of z equals to 1 by under root 2 pi times e to the power minus z square by 2, where z goes from minus infinity to plus infinity and is called the standard normal density function. The graph of the standard normal density function, called the standard normal curve, is shown in image 6. As for all normal curves, the total area under a standard normal curve is equal to 1. Because a standard normal variable z has mean 0 and standard deviation 1, its values are in units of standard deviation from the mean, which are called standard units. We have already seen that if z is a standard normal variable, then its density function is given by f of z equals to 1 by under root 2 pi times e to the power minus z square by 2, where z goes from minus infinity to plus infinity for any z greater than 0. If we define f of z equals to integration goes from 0 to z, f of t dt will be equal to 1 by under root 2 pi integration 0 to z of e to the power 1 by 2 t square dt. Then function f of z represents the area under the standard normal curve between z equals to 0 and z is equal to small z. As the area under a normal curve represents the probability, the function f of z represents the probability when the variable z, capital Z, varies from 0 to small z. Probability of 0 lesser than z equals to f of z. This is equal to integration goes from 0 to z ft dt. Table standard normal curve given the area under this corresponding to probability of 0 lesser than z for values of z varying from 0 to 3.99. To illustrate the use of this table, let us find the probability that z lies between 0 and 2.2 in the first column and then move across the row to the column labeled 0.07 where we read it 0.4884. This probability of its 0 lesser than z lesser than 2.27 equals to 0.4884. We'll see one example. Find the area under the standard normal curve which lies first to the right of z equals to 2.70, second to the left of z equals to 1.73, and third to the right of z equals to minus 0.66, fourth to the left of z equals to 1.88. Let's see the solution. We have an image here. So first, for the first part, required area will be, that is equal to probability of z greater than 2.70 will be equal to 0.5 minus p probability of 0 less than z lesser than equal to 2.70. That is, the total area to the right of the mean is 0.5. This is equal to 0.5 minus 0.4965 equals to 0.0035. Since 0 is less than 0.4965 is lesser than equal to 2.70. Second, required area is equal to probability of z less than 1.73. That is equal to 0.5 plus probability of 0 less than z less than 1.73. Since total area to the left of the mean is 0.5, So this is equal to 0.5 plus 0.4582, which is equal to 0.9583. Since 0 is less than 0.4582, less than 1.73. Third, required area. Probability of Z greater than minus 0.66 equals to 0.5 plus probability of minus 0.66 less than Z less than 0. Since total area to the right of the mean is 0.5, so this is equal to 0.5 plus probability of 0 less than Z less than 0.66 by symmetry. This is equal to 0.5 plus 0.2454, which is equal to 0.7454. Since 0 is less than 0.2454, which is less than 0.66. Fourth, required area will be probability of Z less than minus 1.88, which is equal to 0.5 minus probability of minus 1.88 lesser than Z lesser than 0. Since the total area to the left of mean is 0.5, again we have this equal to 0.5 minus probability of 0 less than Z less than 1.88 by symmetry. So 0.5 minus 0.4699, which is equal to 0.0301. Since minus 1.88 is less than 0.4699 less than 0. If X is normally distributed with mean mu and standard deviation sigma, one might think that a separate table of area is needed for each pair of values of mu and S or sigma. Fortunately, this is not the case, but one must first express a given area as an equivalent area under a standard normal curve. This involves transforming X into a standard normal variable Z with mean equals to 0 and standard deviation equals to 1 by using the following change of variable formula. The formula is Z equals to X minus mu upon sigma. So this is equation 1. The new variable Z will always have a mean 0 and standard deviation 1. Thus formula 1 converts units of X to standard units Z values. Observe that whenever X is between the values X equals to X1 and X equals to X2, the random variable Z will lie between the corresponding Z values, that is Z1 times X1 mu by sigma and Z2 times X2 mu by sigma. Since all the values of X falling between X1 and X2 have corresponding Z values between Z1 and Z2, the area under the X curve between the ordinates X equals to X1 and X equals to X2 equals the area under the Z curve between the transformed ordinates, that is Z equals to Z1 and Z equals to Z2. Hence, we have probability of X1 lesser than X lesser than X2 will be equal to probability of Z1 lesser than Z lesser than Z2. We have thus reduced the required number of tables of normal curve areas to one, that of the standard normal distribution. We'll see one example. A random variable X is normally distributed with mean mu equals to 12 and standard deviation, that is sigma equals to 2. Now find probability of 9.6 lesser than X lesser than 13.8. Given that the area A equals to 0.3159 for Z equals to 0.9 and A equals to 0.3849 for Z equals to 1.2, where Z is the standard normal variate. Let's see the solution. The standard normal variate Z is given by Z equals to X minus mu upon sigma. That is equal to X minus 12 upon 2. So for X equals to 9.6, Z equals to 9.6 minus 12 upon 2, that is equal to minus 1.2. And for X equals to 13.8, Z is equal to 13.8 minus 12 upon 2, which is equal to 0.9. The probability of 9.6 lesser than X lesser than 13.8 will be equal to probability of minus 1.2 lesser than Z lesser than 0.9. That is equal to probability of minus 1.2 lesser than Z lesser than 0 plus probability of minus 0 lesser than 0 lesser than 0.9. So this is equal to probability of 0 less than Z lesser than 1.2 plus probability of 0 less than Z less than 0.9 by symmetry, which will be equal to 0.3849 plus 0.3159. So that is equal to 0.7008. Let's take another example. In a sample of 1000 items, the mean weight and standard deviations are 50 and 10 kg respectively. Assuming the distribution to be normal, find the number of items weighing between 40 and 70 kg. So let's look at the image. Let's see the solution. Let x be the required normal variate representing the given distribution. Now converting x into standard normal variate z by means of the transformation z equals to x minus 50 upon 10, we have for x equals to 40, z equals to 40 minus 50 upon 10, which is equal to minus 1. And for x equals to 70, z equals to 70 minus 50 upon 10, which is equal to 2. That implies that probability of 40 lesser than x lesser than 70 will be equal to probability of minus 1 lesser than z lesser than 2, which is equal to probability of minus 1 lesser than z lesser than 0 plus probability of 0 lesser than z lesser than 2. So this is equal to probability of 0 less than z less than 1 plus probability of 0 less than z less than 2. So by symmetry, this is equal to 0.3413 plus 0.4772, which is equal to 0.8185. Let's say another example. Time taken by a construction company to construct a flyover is a normal variate with mean 400 labor days and standard deviation of 100 labor days. If the company promises to construct the flyover in 450 days or less and agrees to pay a penalty of rupees 10,000 for each labor day spent in excess of each 450, what is the probability that the company pays a penalty of at least rupees 2 lakhs? Let's see the solution. Let x be the random variable denoting the time in labor days taken by the construction company to construct the flyover. Then x is normally distributed with the mean mu equals to 400 and standard deviation sigma equals to 100. Now convert x into standard normal variable z by means of transformation, which is z equals to x minus mu upon sigma. Now since the company agrees to pay a penalty of rupees 10,000 for each labor day spent in excess of 450, therefore, for paying a penalty of at least rupees 2 lakh, company takes at least 2 lakh upon 10,000, which is equal to 20 extra labor days. This company takes a minimum or 450 plus 20, that is equal to 470 labor days to pay a penalty of at least rupees 2 lakhs. The probability that company pays a penalty of at least rupees 2 lakhs is probability of x greater than 470. That is equal to probability of z greater than 470 minus 400 upon 100. Using equation 1, probability of z greater than 0.70 is equal to 0.5 minus probability of 0 lesser than z lesser than 0.70 is equal to 0.50 minus 0.2580, which is equal to 0.242. Let's see the example number 5. For a normal distribution, the first moment about origin is 35 and the second moment about 35 is 10. Find the first 4 central moments. We have row 1 equals to first moment about origin equals to 35. This implies mean equals to 35 since mean equals to row 1 always. Also second moment about 35 is equal to 10. Second moment about mean equals to 10. Since mean is equal to 35, that is mu 2 is equal to 10. Further, for a normal distribution, mu 3 is equal to 0. Finally, to find mu 4, we know that for a normal distribution, beta 2 is equal to mu 4 by mu 2 square, which is equal to 3. So mu 4 equals to 3 mu 2 square, that is equal to 3 times 10 square, which is equal to 300. Thus, the first 4 central moments are mu 1 equals to 0 always, mu 2 equals to 10, mu 3 equals to 0 and mu 4 equals to 300. Next example, for a certain normal distribution, the first moment about 8 is 22 and the fourth moment about 30 is 243. Find the coefficient of variation of the distribution. Solution. The first moment about 8 is mu 1 equals to x bar minus a. So x bar equals to mu 1 dash plus a, which is equal to 22 plus 8, which is equal to 30. Thus the mean of given distribution is 30. Also the fourth moment about 30, that is the mean, is mu 4 equals to 243. However, for a normal distribution, beta 2 equals to mu 4 by mu 2 square, which is equal to 3. That implies mu 2 square is equal to mu 4 by 3, which is equal to 243 by 3, which is 81. So that implies mu 2 is equal to 9. That implies variance mu 2 is equal to 9. So sigma is equal to under root mu 2, which is equal to 3. Therefore, CV is equal to sigma by x bar times 100, that is equal to 3 by 30 times 100, which is 10%. Example 7. If x is normally distributed with mean 400 and the probability of x 540 is equal to 0.0401. Find its standard deviation. Solution: let sigma be the standard deviation of x. Now converting x into standard normal variable z by means of transformation, z equals to x minus 400 by sigma. We have for x equals to 540, z equals to 540 minus 400 by sigma, which is equal to 140 by sigma. This implies probability of x greater than 540 will be equal to 0.0401. So probability of z greater than 140 by sigma will be equal to 0.0401. That implies 0.5 minus probability of 0 less than z less than 140 upon sigma is equal to 0.0401. That implies probability of 0 less than z less than 140 upon sigma will be equal to 0.5 minus 0.0401, which is equal to 0.4599. That implies 140 upon sigma is 1.75 and sigma equals to 140 upon 1.75, that is 8. Although the binomial distribution is a discrete probability distribution and the normal distribution is continuous, yet it is possible to use the normal distribution as an approximation to the binomial if n is large and p is greater than 0.1. Generally speaking, a normal approximation to a binomial distribution is not good if n is small and p is near 0 or 1. A general rule that one can follow is that the normal approximation to a binomial distribution is reasonable if NP and NQ are at least 5. For example, let us consider a binomial experiment with n equals to 10 and p equals to 0.5. The histogram of the probability distribution for the binomial experiment is shown in the figure. Superimposed on the histogram is a normal curve which approximates it. We now state a theorem that allows us to use areas under the normal curve to approximate binomial probabilities when n is sufficiently large. Let's see the theorem. If x is a binomial random variable with mean mu equals to np and standard deviation sigma equals to under root npq, then the limiting from of the distribution of z equals to x minus np upon under root npq as n goes to infinity is a standardized normal distribution. Let's see an example. If 4% of the light bulbs made by a certain manufacturer are defective, what is the probability out of the 500 light bulbs selected more than 25 are defective? Let's see the solution. With the usual notations, we are given n equals to 500 and p equals to the probability that the bulb is defective, which is equal to 0.04. Now q will be equal to 1 minus p, which is equal to 1 minus 0.04, which is equal to 0.96. Now let x be the random variable denoting the number of defective bulbs in the sample 500. Then x has a binomial distribution with mean mu equals to np, which is equal to 500 times 0.04, which is equal to 20, and standard deviation equals to under root npq, which is equal to under root 500 times 0.04 times 0.09, which is equal to 4.38. It is required to find the probability x greater than 25. Notice that in our example, NP is equal to 20 and NQ is equal to 500 times 0.09, which is equal to 480. Since NP and NQ are both greater than, we can approximate P probability of x greater than 25 with the normal distribution. Converting x into a standard normal variable z by means of the transformation z equals to x minus mu upon sigma will be equal to x minus 20 upon 4.38. We have for x equals to 25, z equals to 25 minus 20 upon 4.38, which is equal to 1.14. Probability of x greater than 25 equals to probability of z greater than 1.14, which is equal to 0.5 minus probability of 0 less than z less than 1.14. So this is equal to 0.5 minus 0.3729, which is equal to 0.1271. Hence, the probability that a sample of 500 light bulbs will contain more than 25 defectives is 0.1271. In previous topic, we illustrate how the normal distribution can be used to approximate binomial probabilities when n is large and np times 1 minus p are both greater than 5. In a similar way to the binomial distribution, as and the mean lambda equals to np gets larger and larger, the normal distribution can be used as an approximation to the Poisson distribution. In fact, we have the following theorem. If x is a Poisson random variable with mean lambda and standard deviation under root lambda, then the limiting form of the distribution of z is equal to x minus lambda upon under root lambda, as lambda goes to infinity is a standardized normal distribution. Next example, the average number of customers in a shop per week is 356. Calculate the probability of there being more than 240 customers in a week. The solution: with the usual notations, we are given lambda equals to 256. Let x be the random variable denoting the number of customers visiting the shop per week. It is required to find probability of x greater than 240. Since lambda is equal to 256 is sufficiently large, we can approximate probability of x greater than 240 with a normal distribution, having mean is equal to mu is equal to lambda, which is equal to 256, and standard deviation is equal to sigma, which is equal to under root lambda, which is equal to under root 256, which is 16. Now, converting x into standard normal variable z by means of the transformation z equals to x minus mu upon sigma, which is equal to x minus 256 upon 16. Now, we have for x equals to 240, z equals to 240 minus 256 upon 16, which is equal to minus 1. That implies that probability of x greater than minus 1 is equal to probability of z greater than minus 0. So, that is equal to 0.5 plus probability of minus 1 lesser than z lesser than 0. This is equal to 0.5 plus probability of 0 less than z less than 1, which is equal to 0.5 plus 0.3413, which is equal to 0.8413. So finally, we have learned today normal probability distribution. In this script, we have discussed its meaning, probability density function of a continuous random variable, properties of normal distribution, standard distribution, normal approximate to binomial distribution and its theorem, and also normal approximation to the Poisson distribution and its theorem. We have also discussed how to calculate standard values and also find areas under the normal curve, and understood how to apply the normal distribution to discrete series. So that brings us to the end of today's episode. We are ending here the chapter of normal probability distribution, and we'll see you again discussing about our next topic on Poisson distribution. Till then, take care and have a nice time. Thank you and bye.